Hey folks, welcome back to graphing linear equations, part 2. In the first video we left off just having finished this graph, and it took us quite a long time. I don't know how long that video is. It's got to be 25-30 minutes just to get like data points and the graph ready to go. I know that might seem a little ominous, but I promise you once you've done some practice, this will go so much faster. You'll be knocking these things out quite honestly in like 5 minutes. But I want to show you the associated calculations that go with these graphs now. We're trying to find an equation with all of this goodness that we've put on the graph. I love it. So what we want to do first is find the slope of the best line. We call that best slope. We would give that a heading. We would underline with a ruler. And what we want to do is we want to pull the rise and the run off of our best slope triangle. So don't get the two triangles mixed up. It's always nice to maybe do them in different colors like I did. So here's the number. I did the calculation for you already. Rise over run. My calculator spit out 0.44706 meters per second. Now I should point out with the calculator, you have to be a little bit careful that you get your brackets on the top and the bottom. So maybe I should actually change this in my notes. This is how you have to type it in. You have to make sure that the subtractions happen in brackets, just so we don't end up with a bed mass issue on the calculator. And it spits out that number. We want to record lots of sig figs. So just like feel free to kind of go a little bit crazy. Take lots. I've got like 5. I'd say take at least 5. So take lots of sig figs. Make sure you got your units on there. Then we take our max slope. We do the same calculation. Rise, so we show those numbers, divided by the run. We show those numbers. You don't want to just show the answer. You want to show people where the answer came from just so they can match it up with your graph. And I jumped ahead a little bit. I got 0.521212 with a bunch of repeating decimals there. I want to take lots of sig figs. So both of those values, just kind of go crazy with your sig figs. Take 5, 6, 7. Make sure you got your units on there, meters per second. And now what we're going to do with those two numbers is find something called the slope uncertainty. So our final answer is actually going to be our best slope. But we're not really sure if that's exactly what the slope is. So to get your slope uncertainty, it's a very easy format. You simply take your best and you take that away from the max. So it's the maximum slope minus the best slope, which is going to be 0.521212 minus, this is mine anyways, yours might be a little bit different. Remember, we all drew unique lines and had unique slope triangles. So if I plug that into my calculator, let's see what it gives me. 0.521212 minus that previous answer, I get 0.07415. 07415. Want to put units on there. It's meters per second, rise over run. And we want lots of sig figs still. So now we're going to take the best slope and the slope uncertainty and we're going to tack those things together. When we go to do the overall slope, like just slope, here's the format for this one. It is your best plus or minus the slope uncertainty. So the format's going to look like this. Our best slope was my best slope, put yours in, was 0.44706. Plus or minus the difference between the two slopes, which mine came out at 0.07415. But then remember, with uncertainty, we're only allowed to show one sig fig. So that means I have to cut the thing off right there. My uncertainty becomes 0.07. I now have to match decimal places on my best slope. 0.07 is 2 decimal places, so I have to cut mine off, my best slope, at 2 decimal places. The 7 will round the 4 up. So that looks like a 0.45. And then you want to make sure you've got units on there. Meters per second. So that's the slope with the uncertainty and all tidied up. 1 sig fig of uncertainty and matching decimal places on the actual slope itself. And for the final equation, we're going to go with the format you've seen lots before. I'm going to write it one more time. It's good old math class, linear straight lines, y equals mx plus b. Now what we're going to do with this final equation is we're not going to use y, because we don't actually have a y-axis. We gave it a different name. We called it distance. So again, you can write the whole word, or you can just put d for distance. It doesn't really matter to me. Maybe I'll split the difference. I'll say distance is equal to, now m is your slope, which is here in purple. It's all of the information we've got there. It's the best slope plus or minus the slope uncertainty and the units. And just because that's kind of long, I like to put it in brackets just to keep it separate from anything else in that equation. But you want to list the whole thing. So best slope plus or minus the slope uncertainty with your units. So there's the big old slope. And then we don't really want to put an x in there because we don't have an x-axis. We gave it a different name. We called it the time axis. So that's multiplied by time. And if you think about b is the y-intercept. Sorry, let me get that out of there so it doesn't look so silly. B is the y-intercept, but if you scroll up to our graph, look at how close we are. That's basically 0. So what we're going to do is if you're really, really, really close, we're not going to worry about a y-intercept. So for me on this one, I would say, hey, it's distance equals this slope multiplied by time. I wouldn't even put a b value. You can if you want, if you have a line that crosses way off of the x-axis, but otherwise you don't really need to worry about it. Now what's really cool about this final equation is it tells us that the distance, you can solve for the distance by taking your slope, which is actually the speed of the anteater. It's approximately 0.45 meters per second. And then you can just multiply by a certain number of seconds to figure out how far the anteater goes. Works great because you might want to know how far the anteater has gone for a time value that you didn't test. For example, this. How far do you think it, being the anteater, will travel in 6.4 seconds? Well, we can't tell that from the graph because the graph only goes up to 4 seconds, but we can plug some numbers into our equation now and make it work that way. So here's what we do. How far do we think this thing goes in 6.4 seconds? So I'm going to list my equation again. I'll just put a d for distance equals 0.45 plus or minus 0.07 meters per second. And this time we're multiplying by an actual time value. So that's multiplied by 6.4. So let's go back and talk about some uncertainty rules here. First thing we want to do is actually multiply the 0.45 by the 6.4. Just get a number. So that's 2.88. So that's our guess. We think it's gone 2.88, the anteater, I should say, not it. We think the anteater's gone 2.88 meters, but there is some uncertainty. Remember, when we multiply uncertainty, we have to deal with relative uncertainties, which means we take this uncertainty of 0.07, divide by the number in front, which is 0.45. We have no other uncertainties to add to that, so we can actually close off the bracket, and then we have to remember to multiply by this original answer, which was 2.88. Let's try that out. 0.07 divided by 0.45. Oops. There it is. Multiplied by 288. 0.448. 448. So it's looking like that's my distance. And now we're almost there. We just have to clean this up a little bit. 1 sig fig of uncertainty means the cutoff is right there. And don't play the game when you're rounding. You don't do this. You don't say, oh, 8 rounds the 4 up to a 5, and then the 5 rounds that 4 up to a 5. When we go to round, you simply look one digit over. So I'm trying to figure out whether to keep this 0.4 as a 4 or round it up to a 5. If there's a 4 next door, then it stays as is. So there's my 1 sig fig uncertainty. Now we have to match decimal places, which means 1 decimal point. Here we are going to round up. That becomes 2.9. We want to put units on there so we know what we're talking about. It's now just meters, right? Because we multiplied, this was seconds and the units canceled. The distance the anteater has walked is 2.9-ish, 2.9 plus or minus 0.4 meters. So again, that was very time consuming, 2 videos. I'm sorry for the length of those, but it's kind of a necessary evil. I want you to do some practice with this because you are going to get much, much better. What I want you to try is worksheet 4, number 7. So here it is. Remember, worksheet 4 was the frequency and period calculations. You had only done up to number 6. Now you can do number 7. So there's a data table with some uncertainty, and then a graph on the next page. I want you to make this graph look a lot like the anteater nodes. So give that one a go. You can see that I've already done some of the stuff for you, like the axes are darkened, there's some labeling, but you're going to have to go and title it, and you're going to have to draw your lines with your uncertainty bars, do your big slope triangles. That's a bit time consuming, but use the video and your notes as a guide, and then see if you can get all the way down to the equation. Do check the answers with the answers on the answer sheet, the back of the chapter outline. It's available in the All Resources folder if you need. And don't forget that my answer is not the answer, it is an answer, right? It's just one answer. Everybody's going to get slightly different values. So if you look at my answer and yours is close but not exactly there, then that's totally good enough. So I think you'll see on the back of the chapter outline with the answers, or if you go look online for the full solutions, I get an answer to this question, worksheet 4, number 7, of 10 plus or minus 1. You just need to be somewhere in that ballpark. So if you get a 10 plus or minus 2, or a 9 plus or minus 1, or a 9 plus or minus 2, or some 11 plus or minus 1, then that's all pretty darn close. If you're like way off of this number or way off of that number, then there might be some issues. But you might even get a decimal. Who knows? You could get like a 10.2 plus or minus 0.8, right? As long as you're close, then that's good. So if you need some help, get in touch with me. Maybe fire me an email or come find me at school. Happy graphing.